Okay, so that was the first order derivative. Let's now look at the second order derivative. So how do we get that out of the equations we have? Well, if you look at equation 1 and 2, obviously there's a second order derivative in there. And you can very easily see that if you add these two equations, that now these terms, it's getting very messy with all my drawings here, but these two terms involving the first order derivative will cancel if you make the sum of these two equations. So if you have equation 1 plus equation 2, that actually results in f of x minus delta x minus 2 times f of x, if you bring it to the other side, plus f of x plus delta x. And now we need to divide by delta x squared, as you can see here. Let's bring the equations back. So let's draw another dirty line. So we need to divide by delta x squared. And if we sum the two of them, the next term involving delta x cubed will disappear. So the first one that we have left is delta x to the fourth. But since we divide by delta x squared, this is a second order accurate approximation, plus on the order of delta x squared. Right, of course I should put my dx squared here. Okay, so this is how we can make an approximation of the second order derivative by, in essence, taking a linear combination of values of the function at different grid points. What I'm going to do now is remember, if you cast your mind back to the very first class we did, where I talked about the curl and the divergence and how to interpret that physically and geometrically. I've also talked about the Laplacian, and I told you let's postpone the geometrical approximation of the Laplacian for the time being, and let's revisit that in chapter 3. Now, happily that time has come, so I'm sure you've all been looking forward to that. Now we can really see geometrically what this Laplacian means. Because the Laplacian is, of course, a sum of second order derivatives. So if we look at the 1D Laplacian for the time being, we see that this Laplacian, that this is in fact proportional to, if you just rearrange some constant factors here, this is proportional to f of x plus delta x plus f of x minus delta x divided by 2 minus f of x. This is just simply getting rid of the delta x here and then rearranging stuff a little bit and dividing it by 2. Okay, so now we have an equation. What does this equation tell us? If you were to put this in prose, in words, this tells you that the Laplacian is proportional to what's being represented here. What's the first term and what's the second term? Second term is, of course, the function itself. And what's the first term? How would you describe the first term? The first term is the... Any suggestions? So from the point of view of f of x, what is f of x plus delta and f of x minus delta over 2? That is the... Yeah, that's the average of the surroundings, basically, yeah? So the Laplacian is actually proportional to the difference between the average over the surroundings of the function and the function at the point itself. So this is the definition of Laplacian, or the geometrical interpretation of Laplacian rather. But this is also intuitively easy to understand if you look, for example, at a graph for the case where this second order derivative is equal to 0. If you have a second order derivative which is equal to 0, like for example an inflection point, so let's exaggerate this, this is an inflection point where the second order derivative is equal to 0, there you indeed can see that at the point x, the difference between the function value itself, which is this guy, and the average of the surroundings, which is roughly the average of these 2 points, you will see that there's some symmetry going on, that this average here and the difference with the point itself, that roughly evaluates to 0. So that makes sense from a geometrical perspective. Okay, in the course notes there are some other exercises you can do to, for example, derive find a difference formula for the second order derivative, which is fourth order accurate, and then you need to take into account also terms involving f of x plus 2 delta x and minus 2 delta x, and taking the appropriate linear combination of all of these things such that terms cancel and that you get a nice fourth order accurate approximation of the second order derivative. Okay, but that's the general principle of this finite difference thing. We work on a grid and we replace the derivative by finite differences. Questions so far? So now let's see how we can apply this to photonics, and let's solve a very simple equation. Let's solve the one-dimensional Helmholtz equation. Just to save myself some writing. I will also do a very trivial case, namely where the refractive index is constant. So there's actually no need to use a numerical method to solve this problem, but this is just illustrative. So what is our Helmholtz equation? Our Helmholtz equation is the second order derivative of f with respect to x plus k squared f is equal to 0. So that's the equation we want to solve. And we're not going to solve this in a continuous space with x a continuous variable. Rather, we're going to solve that in a discrete space. So we're going to look for f of x at discrete grid points. So if we do that, we can approximate our second order derivative, and we can write that the second order derivative is f of f plus delta x minus 2 times f of x plus f of x minus delta x. We need to divide by delta x squared. Then we have k squared f, and this thing should be equal to 0. Okay. Oops. Let's be lazy and let's put delta x equal to 1. So let's not worry about convergence. This is just to give an example so that the notation becomes a little bit lighter. So let's make a drawing of what's happening. So we have the x-axis, and we're going to solve, for example, from the interval from x equal to 1 from 1 to 5. So let's say we just have the grid points 1, 2, 3, 4, and 5. And they're separated by 1, so delta x is equal to 1. And we want to figure out what the Helmholtz equation is on this grid here. Of course, we have a second order equation here, so we need some boundary conditions. So let's assume that we fix the value of the field at the point 1 to a certain value f1, which we choose, and here we fix a certain value f5. So this is the problem with the boundary conditions. And then the question is, what is the field at points 2, 3, and 4? So let's summarize all the information we have. We know that f, if we evaluate it at the point 1, it gives us f sub index 1. Okay, that's a rather trivial equation to solve. Let's now evaluate our equation here at the point x equal to 2. So in fact, this gives us f1 minus 2 times f2 plus f3 plus k squared f of 2 is equal to 1. So this is information we get from applying this equation to the point x equal to 2. Let's continue. f2 minus 2 f3 plus f4 plus k squared f3 is equal to 0. And now you see why I only pick 3 interior points, such that we finish rather quickly. The third equation is the following. And then we have its little brother at the end, where we impose that the function at the point 5 gives you f5. So what do we get from all of our efforts? We get a system, a linear system of equations with 5 knowns in theory, although 2 of them are readily apparent. System of 5 equations with 5 unknowns. So this is something we can solve, right? We can go to a computer, we can make use of linear algebra routines, which have been optimized to death nowadays. You can just put it in a computer, let it number crunch, and at the end of the day, or hopefully at the end of the minute or whatever, you get your result. So let's put this in a matrix form to see a bit more the structure of this system of linear equations. So if we were to write this as follows, where we collect all of the unknowns in this column vector. Okay. So like this. We know that the right hand side of our system, we just see that this is, for the first equation it's 1, and then we have 3 zeros, and then we have 5. So what are our coefficients? Well, the first equation is f of 1 is equal to f1. So we have 1 here, and then we have 4 zeros, like this. For our second equation, if we look very carefully what's going on here, we have 1 times f1. We have k squared minus 2 times f2, and then we have 1 times f3, and then 2 zeros. And this pattern repeats itself. You have 1, k squared minus 2, 1. There's a very clear structure going on here. And then finally, we have our trivial case with another 1 there. So at the end of the day, this is nothing more and nothing less than a linear system of equations with the coefficient matrix A, an unknown vector x, and a known right-hand side with B. So we've reduced the problem of solving a differential equation to a much easier problem, one would say, for a computer numerically, of inverting this linear system here. So we need to solve for x. So here you can see how the finite difference method really allows you to solve arbitrary problems on a computer. But remember, it's not exact because we've introduced this delta x here. We've discretized our grid, and this will result in a certain error coming from the discretization, and that's then obviously called the discretization error. And the aim is to find a good compromise between the size of delta x to get a good discretization error and also not too fine in order to avoid wasting computational resources. So this is something you always need to take into account. By the way, as a general piece of advice, if you have a numerical method on a computer and you just run a simulation, that simulation by itself tells you absolutely nothing. I mean, don't trust a single simulation you do, because you need to evaluate what happens with your numerical parameters. It's very well possible that you've chosen a value of the x which is much too wide, and then your simulation is meaningless. So just a single simulation by itself, without any insight in how to choose delta x, is worthless. So at least you need to also verify what happens if I run, for example, with delta x over 2. Do I still get roughly the same results? Then you can have confidence. Otherwise, you have a little bit more work ahead of you. Okay. By the way, there's also a nice quote, I think it was Henning or something, who said that now that we're talking about this order symbol, that the insight you get from computation only scales with the logarithm of the number of computations you do. So it's on the order of the logarithm of the number of computations you do. So also be very aware of what comes out of your computer, out of your methods. Interpret the results. Do they make sense, also from a physical point of view? Okay, I've glossed over the solution of this linear system here. I've just said, okay, you go to a computer and you solve that linear system. There are several ways, actually, in which you can use a computer to solve a linear system. The very straightforward approach is using a technique called direct inversion, which is a technique that you've all seen in your linear algebra courses. So for example, what's the name of the method, the general method you use to solve a linear system of equations? That's called the pivoting going on. Does that name still ring a bell? Gaussian elimination to solve linear systems. Okay, I see at least some people tentatively nodding, so that's good news. So Gaussian elimination, you've probably done that for systems of 3 by 3. I hope you have never done that for systems of 5 by 5, for example, because it's a lot of work. Actually, if you count the number of operations that you need to do, this scales actually with the order of n to the cubed, with n being the size, the dimension of your matrix. So if you make your dimension of your matrix twice as big, then the price you pay for that in terms of computational cost is that it will take 8 times as long to solve your problem. So that's not very advantageous. So the scaling here is very bad. But this is a brute force. It's a very general method. However, have a look at the structure of this matrix. What can you observe if you look at this matrix? What strikes you? Lots of zeros. Actually, this matrix has a certain form, which has a certain name. And the name of this matrix, if I draw some lines here, you will see that all of the action is happening along diagonals. So the main diagonal and then an upper and a lower sub-diagonal. So this matrix is called a tri-diagonal matrix. And I'm sure you can appreciate that if you have a tri-diagonal matrix with lots of zeros, then you can come up with a much more specific approach than Gaussian elimination to make use of the fact that there are all these zeros there, and such that you have a much more efficient way of solving such a linear system of equations. And indeed, there are such methods. They have been developed, and they scale much better. They scale as follows. So they scale with the order of n squared. So now if you have a system which is twice as big, dimension of the matrix, your computational time will be multiplied by 4 as opposed to 8. So that's good news. These are the general methods that you would expect, the straightforward, direct inversion methods. However, there's a whole class of other methods, and they're called iterative methods. In fact, I'm sure there are courses or books dealing only with iterative methods and how to make them work very efficiently. What's the philosophy behind these iterative methods? Well, the philosophy is the following. I've mentioned here that we have a discretization error when we solve our problem using finite differences. So since we already make an error by discretizing the system, the philosophy here is that we also don't need to solve this linear system exactly up to the 20th decimal, for example. So if you have a discretization error which makes that your result will only be accurate up to the 4th decimal, then I'm sure you can understand that you can live with a numerical method to invert a matrix, which, for example, gives you only like 6 digits of accuracy. You don't need to solve this linear system very accurately, and you certainly don't need to solve it much more accurately than your discretization error. So the philosophy here is to construct an approximate of this inverse, and the way this proceeds is that you first start by guessing what the approximate inverse is. So you just guess, okay, I come up with a certain guess of my solution, which I will call, for example, x0, which could be a vector full of zeros if you don't know anything more. It could be a random vector. It could be the solution to a slightly different problem of which you assume that the new solution will be similar. So you start by a guess, and then you sort of refine that guess through some magic, and I will not be able to talk about the magic. You come up with a hopefully more accurate approximation, and then you keep on refining this until at the end of the day you get convergence. Now I've glossed over this step here, this refining step. There are many ways to do this. I've given one example in the course notes of a way to construct such an iterative method. But the important thing here is that you can construct many of these methods in such a way that this step of refining a solution is very fast and very efficient. So at first it seems worrying that you need to take many steps to construct a solution, but if each of these steps can be very efficient, then you can still build methods which, for example, scale with, I don't know, order n, log n, or something like this, depending on how clever you are in constructing these methods. So just giving you a very brief general overview of what iterative methods are. In the course notes, for those of you who want more information, I've discussed a method called the Jacobi iteration. This is interesting for those of you who want to learn more about this, but I'm not going to ask questions about that in the exam. So this is just for those of you who want a little bit more depth and who are intrigued by what I've glossed over here, how this iteration step proceeds. What I've also put in the course notes is a description of a very important, very general method to solve Maxwell's equations in the time domain. It's a so-called FDTD method, the finite difference time domain method. The important thing here is that you start not from the Helmholtz equation, but from Maxwell's equations in the time domain in all its full glory, and you apply the same principle as we did here. You replace the derivatives by differences. In the course notes, there's, I don't know, what, half a page or something describing the essence of the FDTD method. Since we don't have too much space to discuss it in the course notes, it's very well possible that this half a page will not make much sense to you. If you want to know more information about this method, I suggest that you take a different course or read a different book. What I've put down there in the course notes is just a general approximation, general overview of the broad ideas behind that method. But again, I'm not going to ask questions about how FDTD works in detail in the exam. I'm not saying here forget the words FDTD, because it's still a very important method which is used a lot in practice all over the place, and it's important for you to know that this is a finite difference method. Okay, yeah, it's not that difficult to remember. And it's in essence a brute force method, FDTD. You just have space, you discretize it, can be very labor intensive, not for you, but for the PC. And at the end of the day, you get an answer, which you still need to be very careful in interpreting because of discretization error. So bear that in mind. This was an example of a brute force method, FDTD. Any questions about FDTD or finite differences? Before we move on to something which is a little bit more sophisticated, and that's not the finite difference method, but the finite element method. So this is a little bit less brute force. How does the finite element method work? Well, like all good cooks, we follow a recipe, or perhaps good cooks don't follow a recipe, but use their intuition or whatever. Let's not get sidetracked. What's the recipe for the finite element method? Well, the first step is that we're going to have a structure, and we're going to divide that structure in substructures, and the substructures have a name which surprisingly is finite element. So they're called elements, okay, very general term, and they're finite in size. So this is why somebody thought it would be a good idea to call them finite elements anyhow. So if I have, for example, a structure here, like this arch, I could divide this up into elements, like for example a triangular element here, and another element like there. So I could slice this up any way I want, basically, into a number of shapes, elements, discrete elements. So let's suppose we have like k of these elements. So already here you can see a very big difference between the finite difference methods, because the finite difference methods, remember, they had grids, and for technical reasons which I will not go into, it's very difficult to have a grid which is non-uniform. So you really like to have a uniform grid in this case, which makes that you're not very flexible, because you want this rectangular grid here. Here in the finite element methods, you have much more freedom in how you slice up this structure. So for example, you could say, I know from the physics of my problem that here in this region, the field will vary a lot. So here I can have lots of little elements because I want a lot of spatial detail here. And here, for example, I'm pretty sure nothing exciting will happen. So perhaps I can get away with using much coarser elements. So this is a degree of freedom you have. This is an important advantage of a finite element method. So first of all, it's very flexible in terms of locally increasing the resolution of your scheme. And there's another advantage of this structure, of this method, that's especially when it comes down to working with curved structures. Oh yeah, not what I wanted to draw. Let's have another go. A curved structure like this. So I hope you can appreciate that if I have a curved structure like this, and I put a grid over that curved structure, like this. So of course, when I solve this problem numerically, at each of these grid points, I need to pick a certain value of the refractive index. So this will result in the fact that rather than having a smooth curve, what I make with this method is a so-called like staircasing approximation of my structure. So rather than having smooth boundaries, I have these staircased boundaries. So that's not an awfully good approach, but with a finite element method, you can do a lot better than that. because here you can only pick horizontal or vertical lines to approximate a curved boundary. In the case of finite elements, you can work, for example, with triangular shapes, and you can have an orientation of this triangular line any way you want, basically. So you can see that this is a much better approximation of a curved boundary, simply by having the flexibility of shapes of these elements here. So that's a second important advantage of a finite element method. Okay. Now we're going to proceed with the next step in our recipe, and that's that we're going to focus on each of the elements individually. So in each element, what we're going to do is we're going to write down our function which we're trying to calculate. So let's stick to 2D scalar for the time being. So we're going to write our unknown function. Surprise, surprise, we're going to write this as a series expansion of basis functions. So we have a set of basis functions, f sub I, and they're known basis functions. You pick them any way you want, preferably in an intelligent way. And they have, of course, expansion coefficients, and these expansion coefficients, that's the name of the game, they're unknown, and you want to calculate their value. Very importantly, the summation over I terminates at a finite value m, because otherwise, if it goes all the way towards infinity, your computer will run out of RAM or disk space or whatever. So we need to truncate this series expansion somewhere. So that's another important step. The next step we're going to do is, okay, so far we focused on each element individually, and in each element we're going to write down a series expansion like this. What we're going to do in the third step is bringing all of the elements together. So we'll connect them and we'll apply the boundary conditions. So in the boundary conditions, we'll basically connect all of the elements. So for example, for certain field components, you can ask that you have continuity. So all of these continuity conditions, they enter in this third step, bringing all of the elements together. The most important step, which is the crucial part of a finite element method, is the fourth step. And the fourth step is a bit magical at first sight, but later on we'll put more substance to that fourth step. Is we're going to construct a certain quantity based on all of the information we have. For example, we're going to look at a certain entity J, which could often be, is often the total energy in your system. So we're going to construct a certain function, which is, for example, the energy of your system. And of course, this thing depends on the parameters, the unknown parameters A sub I. So often this is the energy, but this does not need to be the case that this is the energy. So here we make a very big conceptual leap, right? So what we're going to try and do is solve a differential equation, but we completely forget about the differential equation. Rather, we introduce this mysterious quantity J, often energy, and we're going to work with that quantity. What we're going to do in the final step, which is something which makes sense from a physical point of view if J actually means energy, what we're going to do in the fifth step is minimize this J. So from a physical point of view, what we're going to ask is that we're going to look for fields, for A coefficients basically, which minimize the total energy in your system. And then from a physical point of view, you can understand nature likes to be lazy, so it's very possible that this indeed gives us the correct solution to the differential equation. But we haven't touched the differential equation. I will not be touching the differential equation when we're trying to solve a problem using finite elements. So this is a bit of the magic of the methods. How do we minimize this J? Well, it's very straightforward. We just as you minimize other problems, you take the partial derivative of J with respect to your coefficients AI. You put them equal to 0, and then you replace this for all. You repeat this for all unknowns that you have. This method here of taking partial derivatives and putting it to 0, this is called the Rayleigh-Ritz method. So it's very important in finite element methods. Because what you do here, if you take the derivatives with respect to a sub I, you put it to 0, you repeat that I times, you have, for example, how many, let's say you have 10 unknowns in your system, then you have 10 equations, 10 unknowns, and then you can solve that. So this is how you again, especially if this is linear, and we need to see that this is linear in the examples we're going to study. Then you get a linear system of equations. You can again go to your computer, use LAPACK or whatever library you have at hand to efficiently solve these problems. And then you have your solutions. Out of that follow your unknown coefficients, a sub I. So this is in very general, broad terms, the philosophy and the recipe behind finite element methods. However, I realize this is extremely abstract, so let's try and make this a bit more concrete by again solving the 1D Helmholtz equation, or indicating how you could solve the 1D Helmholtz equation making use of finite element methods. So the 1D Helmholtz, I've already mentioned this also in the previous example. So this is the equation at hand, right? So let's follow our recipe. First step in the recipe was fixing the finite elements. Now, in this case, our space is just a line here. And let's say, okay, for our finite elements, we're just going to take little segments with constant delta x. So we're going to slice it up like this. This, in fact, is the same approach we took with the finite element methods, the finite difference methods, but it's interpreted slightly differently. This is seen as a collection of elements. Okay, and they could be different in size, but we're not going to do that to make our life a bit easier here. The second step is we're going to try and write our unknown function, psi, as a sum of basis functions, known basis functions. Question is, what would be a good choice for basis functions? Well, let's forget about basis functions for the time being, and let's say, okay, I would like to construct solutions to my problem where I will use linear interpolation between the different values. So for example, I'm looking at certain edge points of my element, so for example x1 and x2, and actually what I'm only going to calculate is psi1 and psi2, and I'm going to be satisfied with just having linear interpolation between all of the intermediate values. If you say this, it turns out that this is in effect equivalent to writing your unknown function psi of x as a sum of basis functions, namely, for example, a basis function x2 minus x divided by x2 minus x1, and another basis function which is x minus x1 x2 minus x1, because these are very interesting basis functions if you draw them. So again, I have here my x1 and my x2. So what happens if I fill out, for example, so let's call this the basis function f1 of x, and let's call this f2 of x. If I fill out x equal to x1 in this diagram, in this equation, you will see that I get 1. So this is a function which is unity here. And if I fill out x2 in this first function, you get 0. So this is a function which goes like this. So this is a function f1. And you get something very similar for the function f2, which is 0 if you fill in x1, and which is 1 if you fill in x2. So these are my two basis functions. Based on the behavior of these basis functions, I can already know what my expansion coefficients should be, because indeed this will then mean that my first expansion coefficient, my a1, is actually psi1 over here, and my second expansion coefficient is actually my psi2 over there, simply because of the behavior of this function. So if I fill out x1 in this formula, I indeed get psi1, and if I fill out x2 in this formula, I indeed get psi2. So this is a case where you can give a physical interpretation, a physical meaning of these expansion coefficients. That's not always possible, but in this case you can do that. So here I've translated the concept of I want to use linear interpolation between my values at the edges of my elements, I've translated that concept into expanding my function in this family of two basis functions. Right. Everybody still with me? Step 2. Let's take step 3. Remember, step 3 was all about bringing the different elements together, because so far what we've been doing is we've considered each element separately. So I have an element which has, for example, an edge point, and I will number these edge points 1 and 2. In this element, I will use my expansion and basis functions that I've just discussed. And then I have a completely different element. I will number my points there 3 and 4. So completely different points, different elements. We consider them all separately. They have no relationship with each other whatsoever. So this numbering scheme, 1, 2, 3, 4, 5, 6, which I've introduced here, I will call this the disconnected numbering scheme, for obvious reasons. Now we know that these elements, they're not floating individually in space. We know they're actually connected. They're lying next door to each other. So we know, for example, that what we have in practice is the following, where these 2 points, they're actually the same, and also these 2 points are the same. So if we assume that we're looking for continuous functions, and we can basically introduce another numbering scheme, 1, 2, 3, 4, which is a connected numbering scheme, where we make use of the fact which elements are neighboring on which other elements, and how do we connect them to each other. Now we're going to do something which seems which seems overly complex for what we're dealing with, but I will explain in just a minute that for more realistic situations, this is indeed something worthwhile doing. And it all boils down to the fact that if we want to solve this problem on a computer, we really like to work with matrices. So how can we bring matrices into this particular discussion here? Well, we're going to write down a matrix which relates the disconnected numbering scheme to the connected numbering scheme. So for example, for the disconnected numbering, we're going to look for expansion coefficients, which in the disconnected numbering scheme are these 6 guys. Let's put a disconnected suffix here to draw the attention to that. And we want to relate them somehow to other coefficients which are in the connected numbering scheme. So what's the relationship between this connected numbering scheme and this disconnected numbering scheme? Well, you can find a matrix for that, because you know that psi1 here in the disconnected numbering scheme is the same as psi1 in the connected numbering scheme. So we can put 1 here, and then all the rest is zeros. Psi2 in the disconnected scheme, is psi2 in the connected numbering scheme. So here we put another 1, and all the rest is zeros. But now it gets fascinating, because we see that psi3 in the disconnected numbering scheme all of a sudden becomes psi2 in the connected numbering scheme. So here we again need to put our 1 in the second column, and so on and so forth. So if you repeat this, you essentially at the end of the day get a matrix which looks like this. And this matrix is called the connection matrix of your system. And it's just a way with linear algebra to basically glue all of your elements together. If you solve them individually, you get values which are in the disconnected numbering scheme. You can bring them in a connected scheme by having this matrix work on them. Again, I fully agree with you that this is completely overkill for the simple 1D case that we have here, because here it's immediately obvious which elements are neighbors of which other elements. But try to imagine that you're working in a 3D case where elements are actually little volumes. Then you can imagine that the bookkeeping of trying to keep track of which elements border on each other, this is much more complex, and therefore the connection matrix will be much less trivial. But the connection matrix is in fact a very efficient way of doing this bookkeeping on a computer of which element actually borders on which other elements. So this is why I introduce it here. Right, now it's time for this magical step. this J thing. So this is really the crux of the finite element method. So J, how do we come up with the function J? Well, I've hinted at the fact that this is often something which is related to the energy of your system. So let's try and calculate the energy of your system based on Maxwell's equations. Now if we take that definition and if we go back to your books detailing all of your equations from electromagnetism, you basically have the following equation here, right? The 1D case, this is the equation which gives you both the energy in the electric fields and the magnetic field. So this is like the total energy in your system. Okay. What we're going to do now is make use of the fact that D is of course epsilon E, B is mu times H, and we're also going to assume that we're working in lossless media, meaning that epsilon is real value, so there's no imaginary part to epsilon. So under that assumption, we can write this energy as 1/2 the integral over our entire elements. In this case, we calculate the energy in the elements, 1/2 epsilon, the magnitude of E squared. I've also gotten rid of the vectorial character here, minus mu the energy, the modulus squared of H. So this is our expression for energy. So we have E and we have H. Of course, they are related to each other. If we take the curl of H, and if we say, okay, there's no current here going on, also current would be confusing because it's also written with a J. That's not the main reason, of course. But we know that this equation holds. One of Maxwell's equations giving you a relationship between E and H. So you can calculate E from H simply by doing 1/J omega epsilon, the curl of H. So this is the relationship between these two guys. Now remember here we're working in the scalar case, and let's assume a TM polarization, just as an arbitrary choice. And let's assume that we can then write down our vectorial H field as just a scalar H field along the Z axis. And this H, in fact, that's the psi that we're going to calculate using our finite element method. Okay. Now, if we make that assumption of scalar Tm, then we need to calculate the curl of H in order to get E. Now, the curl in our trivial case here, IJK, since it's a 1D system, there's only stuff happening along the x direction. So dy and dz, they're equal to 0. And since we only have a component of H along the z direction, we only have this non-zero element over there. So the upshot of all of this is that you can finally write down that J is 1/2 of the integral. So we have epsilon and then the square of E. So this is 1 over, and then we have omega squared E squared. If we take the magnitude squared of E, and then the only term that we have here in our curl is the H dx squared. So this is the first term, and the second term we keep as a function of H dx. Okay. So now I'm going to take a little step without proof, and we're going to say to you that if you have a lossless system, and indeed we started from a lossless system, then you can replace this magnitude squared by basically just a regular square. This is without any proof. And also to simplify our life a little bit, since we're going to minimize J, minimizing the energy in the system, it doesn't hurt that we multiply the expression here by a constant factor. So I'm going to multiply everything by omega squared epsilon 2, just to get something which is a bit more amenable. And then finally we get for our new j that this is equal to the integral of just h dx, the regular derivative squared, minus k squared. These then all combine together with mu to form k squared h squared. So this is the integral. This is the energy of your system. And remember, basically we called this h, that was the psi that we were working with. So this unknown function, this is the energy of your system. Okay, so now we've calculated the energy in your system, and we're going to proceed by minimizing the energy in your system. And then we're going to say this will be a solution to Maxwell's equations. In this particular case, you can understand that from a physical point of view, that minimizing the energy will give you a solution to your system. However, if you're a mathematician and not a physicist, then you're a bit uncomfortable here, because okay, you make that claim, but it's difficult to substantiate. But don't worry, later on I will give a completely different proof to show that minimizing this mysterious j guy over here, that this indeed will give you a result that's actually also going to be a solution to that differential equation. So later on we're going to prove that also purely mathematically. But for the time being, let's just focus on the physics of the problem. But this is the most important part of the recipe of the finite element method. And then I have a step which is step 5, I guess, which is then just minimizing the whole thing. Again, in order to minimize this, it's good to write this involving matrices, because matrices is something a computer can easily make use of. So let's see how we can bring matrices into the calculation of j and also its derivative. So let's focus on a single element first. So for one element, we know that psi, we've written this as sum of basis functions, here expansion like this. So what are the knowns and what are the unknowns? The knowns are of course the basis functions. We have these linear interpolation functions, and the unknowns are our expansion coefficients, which in this case happen to be coinciding with the value of the function at the boundary points. How do we calculate the energy in a single element? So let's call this the energy in the element I. Well, I'm not going to do that explicitly. Let's just focus broadly on the structure of the solution. So what will this entail? It will entail taking the derivative of these functions. So we have these functions, you know what they look like analytically. These are these guys. You can take their derivatives. This will give you a certain slope. You can plug this in all of these equations. Later on you have to subtract k squared, psi squared and stuff like that. So but the important thing is that since you have all of these squares going on, like also squaring what the field looks like, you will get something which will also involve the square of psi 1 and psi 2, as well as the cross terms. So you will have a very complicated expression, but it will be something which is proportional to phi 1 squared, another thing which is proportional to 2 squared, and then another term which is a mixing term, which is the psi 1, psi 2. And these guys are very complex to calculate analytically. Okay, it's possible, and if you want to solve that on a PC, you need to go through that actual work of writing down the equations, programming them, and debugging them. But the general broad structure of this J is this particular structure, simply coming from the square here and also the square there. If you square this, you get indeed the structure involving these terms. So, coming back to our wish of writing this as a matrix, we're going to write this as follows: psi 1, psi 2 in the disconnected numbering scheme, because we're still disconnected. We can write this as a 2 by 2 matrix in here, and then we have again our friends psi 1 and psi 2. And again, this is disconnected numbering scheme. So you see, if you evaluate this, this simple linear expression here, that you indeed get something which has this particular form. Okay, so this is a quadratic form. I'm sure you've seen this before. Okay, so this is just the energy in your system. The A's and the B's and the C's we know, just again by solving this integral stuff, by calculating. The psi1s and the psi2s, these are still the unknowns. This is the energy in a single element. If we want to calculate the energy in all of the elements, you can basically write down the following. You just sum the energy up over all the elements. But again, we have the wish of doing that in a linear algebra fashion. So in essence, you can also write down J as something which will look a bit unwieldy, but which is still useful for a computer to handle, as the following expression. So we build a big matrix consisting of all different sub-elements. So we have psi1 in the first element and a psi2 in the first element. And then you have a psi1 in the second element and a psi2 in the second element. Psi1 in the third element. Okay, you get the picture like this. This is all in the disconnected numbering scheme. Building a matrix. So the first is a matrix A1, B1, C1, D1, dealing with the first element. And then if you write this out for yourself, you can basically see that this following statement here is completely equivalent to what I'm writing down here. You build actually this block diagonal matrix, and then you have these guys. You have the same things here, but in a column vector. Again, this looks a bit more unwieldy, but for a PC, if you want to work with a computer, this is much more straightforward to do it like this. Because, what's now the crucial step? Because we still haven't made use yet of the fact that these are all connected elements. Here we have the disconnected numbering scheme. So we have a very complex expression which is, takes a lot of space to write down, but it basically involves the disconnected numbering scheme. Luckily, we know the relationship between the disconnected numbering scheme and the connected numbering scheme. We've just applied that or derived that up here. So it's in essence a connection matrix. So you can understand that by throwing the connection matrix into the mix, and again, I'm not going to write it down in detail, I'm just trying to sketch broadly how the scheme proceeds here. By throwing the connection matrix into the mix, you get an expression where then everything is written down in the connected numbering scheme, which will also contain a much smaller number of elements, obviously, which is important from a numerical point of view. If you want to solve a system, it's much better to solve that system with as few variables as possible, and by exploiting the connections within the system. That's exactly what you do. Okay. There's a lot of work to just say how we could calculate the energy in your system, this J, but finally we get rewarded by the fact that we can apply our Rayleigh-Ritz method, and the Rayleigh-Ritz method is taking the energy, taking its derivative with respect to all of our unknowns in the system, and putting that energy equal to 0. What's the general form of such a thing? Again, I'm not going to write it down. But if you just look at the general form of the energy here, you will see that if you take derivatives either with respect to psi1 or psi2, what you end up with is a linear equation. So that's good news, because this procedure will give you, for example, m linear equations with also m unknowns. And then you can go back to your computer to solve this problem with a standard numerical method. So that was a lot of work. So I hope you realize by now that implementing a finite element method is much more difficult than implementing a finite difference method. I think it's very possible for you guys to implement a very simple 2D FDTD in, let's say, an afternoon or something like that. It's really straightforward. It's very easy to program. But if you run an FDTD, that takes a long time. So it's very labor intensive. Whereas this particular method, finite element, I've introduced you to the fact that this has many advantages in terms of flexibility of grid and then runtime and being more accurate and stuff like that. But the price you pay for that, or at least the price the programmer pays for that, is that it's much more complex to implement. So this is not something you write in an afternoon, as I'm sure you can appreciate from the broad overview that we've sketched here. And this is, of course, why there are companies who do that work for you and who sell you that software such that you can make use of it. But still, both methods are in use. Perhaps a small little commercial note: if you want the name of a very popular finite element method solver, that's COMSOL. If you want the name of a popular finite difference FDTD solver, that's, for example, numerical. But no endorsement. This is not a commercial. I'm not in any way affiliated with any of these companies. This is not to say that there aren't any other pieces of software out there which will do the job. But these are just two very well-known examples. Okay. Any questions on this general scheme? If not, what I would like to do during the last minutes of this class here is to give you a different interpretation of what we've been doing so far, which will help us to show that there's yet another advantage to doing a finite element technique related to numerical precision and stuff like that. But for that, I will introduce a lot of new terminology. So what I'm about to do is I'm going to give you what's called a variational interpretation of what we've been doing. So variational interpretation. Terminology. I'm sure you all know what a function is, right? So, for example, a 1D real-valued function is an object which takes for breakfast a real number x, and it spits out another real number y. That's a one-dimensional function. There are also two-dimensional functions. What do they eat for breakfast? They take two numbers, they're a bit more hungry, and they spit out, for example, a third number. So these are all functions. They take a number of numbers as inputs, and they give you, for example, in this case, a single number as output. So, but let's focus on them as being just black boxes with an input and an output. These are functions. What are functionals? Functionals are also black boxes, and they also have an input. They also eat something for breakfast. But what do the functionals eat for breakfast? They eat the functions for breakfast. So a functional is something which takes as its input a function, f of x, and then it spits out a number. So these are functionals. Could you come up with an example of a functional? What's a black box that takes a function as input and calculates a number based on that function? Any suggestions? How could you turn a function into a number? What are ways to do that? Yeah, if you take, for example, an integral of a function. So if you have f of x, you can calculate the integral from, say, from 0 to 1, f of x, yeah? And that turns our function into a number. Yeah, that's right. So this is a straightforward way of having a functional. But in more recent memory, is there something that we have encountered which you could interpret as a functional? So what about something like this? This is again an integral, of course, but here it's our j. This mysterious function j we've derived is in fact not really a function, as you can see here. Our j is actually functional because what it takes for breakfast is like a field distribution, and it calculates the energy from that field distribution. in the most common case where J has the meaning of energy. So our J is an object which operates on a function and gives you back a single number. And it does so typically by using integrals. So these functionals, we have encountered them before, it's just that we haven't called them functionals. That's perhaps new terminology. Let's introduce other new terminology, and that's a variational expression. So variational expression. What is a variational expression? Well, if you have your functional here, if I put in, for example, a function psi1, it will give me a number j1. So I can keep on plugging different functions into my functional. And obviously, among all of these functions that I can plug into my functional, there will be one of them which gives rise to the smallest j, the smallest possible j that I can find. And this is a variational expression. The variational expression is asking, okay, I have my functional j, which operates on functions psi, and I'm going to look for functions psi such that when I plug them into my functional j, that they minimize that expression and give me, for example, the actual minimal energy P here. So this is a variation expression. It's minimizing over the family of possible allowed functions a functional such that the end result of the functional gives you the lowest possible result among all of the members of the allowed functions psi. This is a variation expression. How will you solve in practice such a variation expression? Well, there's a small problem here because you need to look for functions. A function, how do you define a function? Okay, you could say I specify what the value of that function is at all of the possible points. But for a continuous function, we have an infinite number of degrees of freedom actually. So this is a quite complex problem. This is a problem with an infinite number of degrees of freedom. And a computer will not like this. So how do we find in practice a function which minimizes our variation expression? What's the strategy we could employ? Based on what we've seen before, what's the strategy we can employ to solve, sorry? Discretization, but do we talk discretization of what? Discretization in space, or discretization of T? So what do we need to discretize, quote unquote, here when we want to solve that problem? In fact, it's not really the space that we need to discretize. We sort of like discretize our psi by replacing it, and again, that's the whole philosophy of basis function expansions. We have known basis functions and we have unknown expansion coefficients. So this is like a way of going from something which has an infinite number of degrees of freedom to something discrete which has a finite number of degrees of freedom. So and then now the problem is reduced to the following problem, where we just take the partial derivative of our j's with respect to all of our coefficients a sub I, we put them equal to 0, and then we have our solutions to minimize this problem. Okay, now we've actually done something subtle. We've replaced our function psi with this approach, with this expression. So here, when we have our new psi, when we apply our Rayleigh-Ritz method, when we introduce our series expansion, do we then actually still have a functional? Perhaps a subtle question. Who thinks yes? Who thinks no? So this is indeed a bit of a subtle question. But actually, what we do by the Rayleigh-Ritz methods, okay, we started out from a j which operates upon a function, and the unknown in this case was the function, infinite degrees of freedom. What we've done now is we have a j which still operates upon a function, but a function which is described by a certain number of parameters. And the parameters here in this case is a finite set, so no longer infinite. So actually, while this expression is a functional, this is actually just a regular function. because what it takes for breakfast are the unknown expansion coefficients a sub I, and based on the unknown expansion coefficients, it spits out an energy. So, a bit of a subtle point, but by applying the Rayleigh-Ritz methodology, we kill our functional and reduce it to a more lowly ordinary function, which takes a finite number of real values as input. Okay. What's a possible problem or a possible complication with just asking that the derivative here is equal to 0 if you want to find a minimum? What could also happen? You could also have a maximum, saddle points, whatever. So this is a bit of a problem. Well, in practice it turns out not to be such a big problem, because if you find a solution for which this condition is satisfied, you can easily verify for yourself if this actually corresponds to a minimum or a maximum just by plotting some neighboring values. So in practice, it doesn't turn out to be such a big problem. Also, because the physics of the problem, typically you have a solution which minimizes the energy. You don't have a solution which maximizes the energy, because this happens for infinite functions. So in practice, you typically get a minimum, and it's easy to verify if you just look at the neighborhood of that function. Okay, you might wonder, why bother? We haven't done actually anything new here. The only thing we've introduced is some new terminology, just some quite pedantic terminology. We've talked about variation expressions, functionals. This doesn't learn us anything new in the context of finite element method. So why do we bother with this? Is there something more to this than just new terminology, which I could use to make myself unpopular and try to impress people? No, actually there is something behind this, because let's have a look at what this variation expression actually means. Say I have a function, psi star, which minimizes my variation expression, j. What does that mean? This means, you can understand that this means that if you move around in the neighborhoods of your solution, let's say, if I move around in the neighborhood of my function psi star, that my variation, that the way my j varies, that this will be very small. It will actually be 0 around psi's in the neighborhood of psi tilde. This is a very similar statement to saying that if I have a function, a regular 1D function, I have a function for which x tilde minimizes, if x star minimizes a certain function f of x, then you also know that the variation, which is another word for derivative here, the variation of my function in the neighborhoods of my solution x star, that this will be equal to 0. Very simple from a geometrical point of view. If I just look at 1D functions, I have x, I have f of x. I have, for example, a function value here. So for x star, I minimize my f of x, which will give me, for example, my a certain value p. What you see here is that if I move around in the neighborhoods of my point x star, the price I pay for that in terms of accuracy on my value for f of x at the minimum, which I will call here p, that will be very small. So if I move around here in the x-axis, based on the fact that my derivative is 0 and that I have a 0 slope here, a flat curve, walking around here in the neighborhood of this function will result in a very small variation for the actual function value. Again, it would be very different if I was sitting at a point where the slope is very big. If I walk around here over a certain distance, then I will have a much wider variation on my y values. But because I'm working in a point where the slope is 0, where you have a flat horizontal curve, the impact of this variation is minimized. So this was just for a case where I have a function with a number as an input and a value as an output. You have to imagine a similar diagram, which is of course conceptual, where like the horizontal axis or the horizontal plane is not a space where numbers live, but it's a space where functions live. And each point in this diagram then corresponds to a function. So just abstractly try and get your head around this. But the same principle applies. If I'm working in a spot where my variation is minimum, where I minimize the functional, then in that case, if I walk around in the neighborhood of that point, meaning if I choose functions which are slightly different than the function which minimizes the functional, that I will still get values out of that functional which are very close together because of the fact that we're working in a minimum here. And that's very important use because this means that my delta j, if my delta j is equal to 0, that the p-value which I calculate will be rather insensitive to errors. And you always make errors. You always make errors in a numerical system because of the discretization, because of the finite precision in your system. So there will always be small numerical rounding errors going on. But since you're working with a variational expression, where you're working at the minimum of a functional, the price you pay for these errors is actually damped. You reduce the impact on the vertical axis. So this is perhaps a bit of a difficult concept to wrap your head around, but think about this for a while, and next week we're also going to revisit this. Before I cut you loose, there's one thing I would like to say. Here, all our variational expressions, all our j's, we typically said that j is an energy, but the power to calculating your system is often not something where people are interested in. People are, for example, more interested in calculating, I don't know, propagation constants, squares. But luckily, there are also variational expressions to calculate the propagation constant of a mode. So you can construct propagational variation expressions where you also minimize a functional j, and the value that comes out is something which you can interpret physically as the propagation constant squared. Okay, but next week we'll continue on this theme of variation expressions, how it benefits the finite element method and stuff like that, and give some more mathematical proofs. So see you all next week.